as Mata said, I'm back in my office in KC, but it was an adventurous day at the airport. And hopefully I will be joining you guys tomorrow. So I'm going to jump right in. My thought is to set the stage and thinking about sort of the state of the sector with solar and state of the research. But the reason I've titled this Examining the Trade-offs is because in economics, we're always thinking about what you give up to get something else, right? So if the goal is to sort of decarbonize the electricity grid, or if you like, just reduce the greenhouse gas emissions coming from our electricity generation, then obviously one of the key ways that we've pursued doing that is with renewable energy development. So I want to think a bit about how some different types of renewable energy development have gone into that, right? How that has evolved in terms of solar, and then think also about some of the trade-offs in terms of the two primary ones, which are wind and solar, and then also just some different types of solar deployments that we could pursue, right? So I am going to put up our USDA disclaimer. But because that's boring, that'll be on the left. And then this lovely image on the right here is one of the papers that myself and some colleagues published this year. And in this paper, we talked about land cover and land cover change, right? So trying to think about what happens to the land in which solar farms or wind farms or utility scale wind turbines are developed. And so I'm going to talk about some of the results from that paper, sort of interspersed with other information from other government agencies on the market for solar, the growth in solar, and the growth in wind. So let's just jump right in with some information from Department of Energy. This is Energy Information Association, and they put out a lot of statistics. And they have been tracking utility scale wind for a couple of decades, at least, probably the mid-2000s, wind really kicked off. So you see this top bar on this graph. We're measuring in capacity, which is gigawatts. I'll get a little bit more into that and what that really means in the next slide. And you can see, right, that we see this really steady growth, just looking at that top bar in wind, going back to 2014. And I will tell you that this growth for wind started much sooner. You could think about even late 90s, start expanding out of California. But the other things you see on this graph are utility scale solar. So solar farms, right? That's the way I'm going to think about this. So we're thinking about solar farms on the leftmost bar here. And then that smaller bar, or not that much smaller bar in 2014, but that's our small scale solar. So rooftop solar is the way to think about that, right? And you might wonder why I picked 2014. That's actually when the Energy Information Association started separately tracking what they called at the time distributed solar, and what in 2017 officially became sort of small scale solar, in recognition of the fact that distributed solar, right, meaning rooftop solar, typically is connected to the grid, right? So this is really about, are we talking about solar farms on the left? Or are we talking about rooftop solar on the right? And whichever one you want to talk about, you can see that they've both been ramping up from 2014 through 2023, right? And if we look at this compared to the entire capacity of the electricity sector, right? So just go across the whole sector, we're going to see that our share moved from less than 1%, right, up to about 7.2% in 2023. So if you look at growth, right, that's 7 times more, right? So big jumps in utility scale solar from less than 1% to 7.2%. If we look at wind, we see a bigger number at the end, obviously a higher bar, 11.6%. But what we notice is that the growth rate is actually much smaller. So from 6 to about 12, right? Not nearly the growth rate. So what we've seen is that wind development, because wind initially was less expensive to roll out, started sooner, but solar development has been outpacing it by a lot. And the other thing that we see on this graph, which is doesn't quite jump out at you as much, but if you look at the share within solar, how much is from utility scale, how much is from small scale. The small scale, the rooftop solar, the share actually declined from 41 to 34%. And the reason is simply that utility scale solar is growing faster. It's not, obviously, by looking at these light pink bars at the end, that small scale solar isn't growing. So they're both increasing in magnitude, but what we're seeing is that small scale solar, right, has been outpaced by the large solar farms. So if you want some a little more just focus on the growth rates, then over this period, utility scale solar, almost 9 times more capacity. Was that far less than 1%? That it from 1 to 7, it went 9 times higher. Small scale, right, didn't quite keep up, 7 times, still a lot more small scale solar. And then from wind, we see that capacity more than doubled. If you go back and you look at wind, I say mid 2000s all the way back to late 90s. If you want to see when utility scale solar started, you're talking maybe after 2007, but the majority of the utility scale solar growth has been after 2016. So wind's an older story and solar's a more recent story, which is part of the reason we're here, right? Renewable energy is growing, but really the focus is on solar because of the growth rate in solar is just so much more dramatic than wind over the last 10 years. So a few definitions. I know we have groups with different perspectives in this room, so I thought maybe we'd have groups with different background. So I'm not going to belabor long definitions. So if some of you have better definitions, you want to share those tomorrow, please bring them with you. But I wanted to give just a little bit of working knowledge of sort of the terms I'm going to use. And one of the things I'm going to say is utility scale. And so utility scale, one shorthand definition from the Energy Information Association, people will say, well, it's just greater than a megawatt, right? The other part of that Energy Information Association definition is that it's also designed primarily for the grid. So you're putting in large scale or utility scale solar or wind to put that generation, like our photo on the left here, to add that generation to the grid. This is not for primarily for your residents, right? Compare that with small scale, which is less than 1 megawatt, right? And that is primarily for providing electricity at the location. But also, if you know anyone or if you yourself have rooftop solar, you know that you can, in a lot of places, spin that back to the electricity grid, right? And you'll get perhaps the same rate, your residential rate, perhaps a wholesale rate back from your electricity provider. So this is providing electricity for your house, but this also typically, not always, but typically folks with small scale are connected to the grid. And the reason is for that reliability, right? So we'll talk a bit more about that. And the other thing I'm going to talk a lot about in comparing both across the different types of renewables and then also from the US to the Midwest, I'm going to be comparing capacity. So if you think about capacity, you could pick a solar panel or one of those large wind turbines, and each of those, think of it as having a stamp on it. That's a number that says this is the maximum amount of electricity that that solar panel or turbine can produce. And then generation is the amount that was produced over a given period of time. If you go to the Energy Information Association, they'll have monthly reports, they'll have annual reports. If you really dig in somewhere, you could probably get daily numbers, right, on different amounts of generation. I focus on capacity. There's not a right answer here. I think of capacity, right, as a stock and generation is the flow. And there could be a lot of factors that are going to affect how much generation you have, including the demand for electricity from consumers. And that could have to do with the weather, right, and other factors. So I think of capacity as a little bit more stable in that sense. And the other thing to consider is that when you're thinking about renewables, the capacity factor, the amount of time, right, that solar panel is actually generating electricity or that wind turbine is generating electricity are going to be relatively low compared to, say, a coal-fired power plant. Just meaning, the sun doesn't shine all the time and the wind doesn't shine all the time. So if we look at capacity, then we're looking, right, at the potential amount they could produce, but we aren't, right, looking at generation, which says how much time was the sun actually shining, the wind actually blowing, so that we were actually getting generation. So again, both of these are going to give you different pictures. I just went with capacity. but there's a lot of information on both of these things from several different sources, primarily Energy Information Association and National Renewable Energy Lab. So what do these numbers mean? Megawatts and gigawatts? Well, there's a few different ways to think about them. One of them is some numbers that I got from a DOE website, which I thought were interesting. So if we assume each one of those solar panels is about a half a megawatt, then it would take 1.9 million of them to make a gigawatt. 294 wind turbines, assuming they're about 3.5 megawatts. And another way to think about it is that the typical US residential customer, you're going to need about 11 megawatt hours per year. So that's a generation number, right? So 11 megawatt hours, right? Meaning that it's a flow of electricity that you would need. But it just gives you some context in which to think about these things. Another way is just a gigawatt is 1,000 megawatts. And there are terawatts, which are 1,000 gigawatts to make a terawatt, and there are kilowatts. It takes 1,000 kilowatts to make a megawatt. I'm going to try and stick with these two, but I may not have that much luck. And I can imagine in our discussions tomorrow, all of these different ways of thinking about generation may come up. So these definitions and some more detailed ones may come back. But there's something to get us started for tonight, so everyone's sort of on the same page when I keep saying capacity and I say megawatts a lot, right? Gives you a little context. All right, so what's driving this, right? We have a lot of solar. We know that that's a big factor, and people are thinking about what does this mean? The other thing, right, of course, that's made this a hot button topic in the last couple of years was the Inflation Reduction Act of 2022, right? $370 billion investment in energy programs. And I just pulled out a couple of numbers from a White House report on the Inflation Reduction Act spending to give us a sense of the magnitude of these things, right? DOE has been funding all kinds of energy development, right? And energy technology for a long time. And this was a big ramp up even for DOE, right? So a couple of numbers out of that White House Act, up to 40 billion in guaranteed loans for clean energy technologies. Now that doesn't just mean solar and wind, that could be nuclear, that could be fossil fuel if it's about reducing emissions, right? But it's still a lot of additional funding for guaranteed loans for expansion of cleaner energy. And then up to 250 billion for guaranteed loans for energy infrastructure, right? And again, that could be more than just we think of solar or wind, but a lot of that is also thinking about clean energy, right? That could be lowering GHG emissions, or it could be also just lowering local pollutants. But it gives you a sense of the magnitude that there's been a big ramp up here in thinking about how do we expand this energy infrastructure. So we already had a big growth in solar going on because costs were coming down, and then we get an infusion, right, of funding to push us forward to try and address, right, this decarbonizing, which some people like to say, or just reducing GHG emissions from the electricity grid. And I'm at USDA, so couldn't leave us out. The Rural Utility Service has up to $1 billion for renewable energy infrastructure loans. This isn't just for farmers, this is for rural businesses as well, right? So thinking about expanding energy infrastructure, say if you want to put a whole bunch of more solar in, you're going to need also additional transmission lines, for instance. And then there's an existing program called Rural Energy for America, which is REAP, and that was supporting a lot in the past energy efficiency projects. Well, here's $2 billion for not only energy efficiency projects, but most of that money that's been spent in the last year and a half has been going toward expanding renewable energy development, right? So people are pushing far forward, right, on thinking about how do we do this transition of the electricity grid to renewable generation. So there's been a lot of research thinking about benefits. And then there's been some research thinking about costs, which I put in here as community concerns. And I'm going to start with some benefits. This is a recent paper, and it was looking at using survey data, just looking at agricultural producers. And we found over the 2011 to 2020 period, average annual number of farmers who received some kind of energy leasing income, right? So could be an energy payment for a lease, it could be a royalty payment, right? But energy payments in general was about 3.5%. But for those farmers, right, some of that was definitely oil and gas income. But we also sort of tried to identify farmers who maybe were more renewable energy. And so one of the things we did was we looked at counties that had wind. We defined a set of wind counties, and we looked in those counties, and we had an average annual energy payment in those counties of about $17,000. So again, that could be leasing payments, one-time payments, right? But it gives you a sense that there are significant benefits to individual producers or landowners who are going to adopt renewable energy, right? There's also literature, and this is primarily for wind. And I will just tell you that's because it takes data to do research, and solar's so much newer that the research on solar is probably coming out this year and in the next few years, right? So looking at the effect of solar on local communities, it will be there soon, but right now there's about 70,000 approximately utility scale wind turbines across the US. There are about 4,000 plus solar farms across the US. And so in looking at this distribution, when people are trying to look at these different effects, one, wind was there longer, and two, it's distributed pretty widely across the US. Not that solar isn't, it's just gotten there a little bit later. So what has the literature found? The potential for lower property taxes, increased employment, increased tax revenue, and sometimes that tax revenue leading to increases in school spending, right? So there could be not only private benefits to landowners who are going to be receiving energy payments for this utility scale wind or solar, but also these benefits to communities from having this development maybe affect the tax base, right? Which could lead to other benefits. And then also anytime there's increased employment in a community, we expect that also to lead to some community benefits, right? And so there's also community concerns going on. And a big one that you're seeing in the literature is this concern about land use change and farmland loss, which was part of the impetus for us writing that paper. And that's particularly for solar. And I'll talk a bit more about land use change differences between wind and solar a little bit later on. The other thing, there's been quite a bit of research on trying to understand if you have a wind turbine on your property, does that increase your property value? Does it decrease your property value, right? And there have been several studies, a lot of them focus on rural communities, and it's sort of been mixed. There's a small negative effect or there's no effect at all. And I can tell you there's ongoing work in this space, both for wind and for solar, and really trying to understand these effects. And one of the challenges is if you're looking at rural areas where much of the wind and solar is developed, those aren't exactly high turnover markets if you're thinking about agricultural land sales, for instance. And so trying to understand or to tease out the effect of a wind turbine versus other factors, right? It's going to take, I think, just continuing on with this research to really understand what is the general pattern, and then are there differences in different areas of the country, right? So there was a research paper that came out just specifically looking at Kansas, and they didn't find an effect there either, right? So, and they were really focused on agricultural land. So it's been a little bit mixed, and I will say the reason people keep thinking about this is because we're surprised that if there's this big of a payment, that we aren't finding an effect on property values. And one of the reasons that people will argue maybe we're not finding an effect is that wind turbines also have been associated with negative outcomes, right? And economists think of these as often as externalities. If you're a neighbor to a property that has a wind turbine, right, you're not getting that energy payment, but maybe you still have to deal with some noise, or if it's a solar farm or a wind turbine, the altered views. There's been history, right, of people looking at the effect on wildlife habitat. I would say siting for wind and solar has evolved over time, but there was certainly concerns, right, that there were negative impacts on the neighbors and positive impacts on the landowners. We're just so far not seeing a lot of that in the research that's looking at specifically at property values. So stay tuned. There will be more to come on that in that section, in that research area. But it's certainly something, if we're thinking about trade-offs, that we'd really want to understand a lot better. So how much solar do we need? And I love to find these photos where it just looks like the solar panels or the wind turbines go on forever. Although if you live on the plains, you realize that it just looks like that here, right? It just looks like it can go on forever. And that's just a nice angle. But how much solar do we need, right? Is it really solar going on forever? And so this is a paper that came out from the National Renewable Energy Lab, and they have a lot of great work in this area. And they were doing a study saying, if we want to achieve net zero greenhouse gas emissions by 2035, what do we need? Right? And there are a lot of assumptions that have to go into these things, you can imagine, in terms of, well, what kind of technological growth would we expect? What kind of transmission line would we also need to add, right? So I just boiled it down to thinking about utility scale solar or solar in general and wind, right? So what do we need? How does that compare with the amount of solar and wind that we've been adding so far, right? So if we look at solar, it's a pretty wide range, and that has to do with the fact that you're making assumptions about technology, right? Nowhere to predict the future, so you're going to have to make some different assumptions, and that's going to give you a range of values of what utility scale solar capacity we would need. So it's between 300 and 1,500 gigawatts. So what that means in terms of adding solar would be that we would need to add 40 gigawatts a year on average for 10 years, right? Well, let's do a comparison, right? In 2023, that was a real stellar year for solar, added 19.5 gigawatts. You would need to double that on average for 10 years, right, to meet this NREL projection, or, you know, to get us somewhere, right, in this range. Obviously, if you were on the low end, it would be lower. The high end, it would be higher. What's interesting to note is 2023 really was a banner year for utility scale solar, because prior to that, 2022, it was 11.4 gigawatts, right? So that's going to be 4 times, right, the amount on average for the next 10 years. So however we look at this, this would be a large increase in utility scale solar, depending on how other technologies come along. Particularly, I'm sure some of you are saying to yourselves, what about battery storage, right? I think there's a lot of questions about where battery storage is going to fit in. I'm sure this will come up again as well tomorrow. But certainly some of the variation here is going to be in how much natural gas, right, are we still using if we're going to go for net zero greenhouse gas emissions, right? Because we could have offsets. How much battery storage are we assuming? How is this solar distributed across the country, right? None of that was in this statement right here. I was just thinking, if we want to think about where we want to go, this is the goal, net zero greenhouse gas emissions, it's going to take a lot more solar, right? It's certainly not going to fill up our rural landscape by any means, which I'll talk a bit about later, but it would be a big ramp up from where we are now. Now, one thing they didn't project into the future was small scale solar. So they assumed that there were 190 gigawatts installed. They have different systems that they're projecting out, utility scale and small scale. And so the small scale for this particular study was not projected. Not to say that they don't have other studies where they're looking at how small scale solar could ramp up. So they just held that steady at 190 gigs. Now, utility scale, again, big jumps. So 1,600 gigawatts was the maximum amount of utility scale. That would be an additional 60 gigawatts per year on average for 10 years. What's interesting here is if you look at 2023, we added 6 gigawatts, right? So that's 10 times as much. But if you look at 2022, what you realize is that we actually added fewer less wind capacity in 2023 than we did in 2022. Why? We added a lot of solar, right? So if we're going to meet this, right, then we're have to continue to add a lot of both of these. And it's just something that I think is important to keep in mind. The scale at which we've already been adding still pales in comparison with what we would need to be doing if we are holding small scale solar constant, but we are assuming that we're going to have some technological growth in a lot of other areas, including battery storage. We still would have a lot more utility scale solar and wind to add. So, okay, we have a lot to add. Well, how much do we have? These are good questions, right? NREL, back to NREL for our answers. So if you look at, again, different scenarios, I think their mid-range scenario, we have 9,600 gigawatts of utility scale solar potential. Currently in the US, we have about 1,200 gigawatts total electricity capacity. So we have a lot more solar, right, than we would need. Rooftop solar, just rooftop. Remember in that last projection, they held it at 190. There's 1,100 gigawatts of rooftop solar. Again, different projection done by NREL, taking into account the amount of actual rooftops, right, that are available for development across the US. And wind. We also have a lot of wind, and this is onshore wind specifically. There's also some forecasts for offshore wind. So all to say, when you're thinking about trade-offs, if we have about 1,200 to 1,300 gigawatts total electric capacity in the US today, there are well more than that if we just looked at potential. This, of course, does not take into account costs, right? So can't be an economist and talk about trade-offs and not talk about costs. So if we're going to put solar, where should we put it? Well, this is a solar irradiance map. This is the one that's averaged across the year. And anyone who's ever been to New Mexico or Arizona is not surprised by where the dark red spots are here, right? Southern California. And then you look at the Midwest and you might think, interesting, I wonder how much solar we have here and why. So hang on to that thought. We're going to come back to it with another irradiance map. The only place where really you just have nothing is Alaska, and that's because, well, it's dark for a good chunk of the year, right? So if you're going to average across Alaska, you're going to get not a lot of sun. So you can see where you would expect a lot of solar, a lot across the south, but you can also see that you have some of these bands of yellow and dark orange, lighter orange, darker yellow going well up, right, across parts of the Midwest. So where would we expect solar? Very hard to say, right? Almost a majority of the country, you could imagine, would have solar growth going on because there's a huge amount of solar potential and because it's widely distributed. So what about wind? What we see with wind is, if I overlaid, and I will later, where we see wind turbines in the US, it's one section like we can think of as the Midwest here. Another a term for this little area that starts at North Dakota and you head straight south and you hit Texas, the plains. Yes, so the wind really does go sweeping down the plains, and there's just a lot of wind turbines here. So you're going to see a lot of wind potential distributed here along the plains. Not surprising, along ridges, you see these very dark blue lines, and also not surprising along the outside of the country. That's our offshore wind potential, right? So wind potential is very much right now overlapping with where we're seeing wind turbines. And the future of wind turbines could be more, right? Taller wind turbines. So when you're doing wind potential, this is at 100 meters above the ground. If you go to 120, it's windier, right? Or maybe you put in smaller wind turbines closer to where they're needed, right? Say maybe you put in a lot more smaller wind turbines. Again, trade-offs. So I don't have costs comparing large scale, utility scale wind and small scale wind because we don't really have small scale wind in the US. But we can talk about in a few slides here, those trade-offs between utility scale and small scale solar. So And also, if you want to know why we might have some solar in the Midwest, I couldn't help but just pick up this one. This is June. So it's sunny everywhere in June in the United States. So there you go. So if you go to June, right, if you aren't doing an annual average, other than Alaska, you're going to have, right, some sun. So lots of factors you can imagine are going to determine where we're going to end up with solar. Solar potential is one, keeping in mind that we just have a lot of solar potential. Policies are another. So you can imagine if a state has policies promoting solar, we might expect to see solar there, right? And there also could be some demand side drivers, right? If people really want to have solar development or they're adopting rooftop solar, sometimes they do it because there's a beneficial policy. Sometimes they do it because of preferences, right? So all that's going to influence our distribution. So what about offshore wind? We also, those dark blue lines around the United States. Well, there was a goal of 30 gigawatts by 2030 and installed as of May 2023, according to Department of Energy, was 42 megawatts. And so this graph on the right, I think is interesting when you see the big ramp ups in solar, the big ramp ups in onshore wind. What we're seeing with offshore wind is actually some that's being canceled. So between May 23 and May 2024, there were cancellations of planned projects, right? So we see on this right, regulatory approvals pending, under construction, a bit of canceled up here in New Jersey, right? So what's going on is there were concerns about higher interest rates, high inflation, and supply chain issues. Suffice it to say that offshore wind has not, in terms of the cost, it hasn't proven, at least based on the data that I've seen, to be in that cost-effective state that you're seeing onshore solar, rooftop solar, onshore wind, rooftop solar, and utility scale solar, right? Those things we're seeing expanding. Offshore wind is still a little bit in that early days of the market where there's a little bit of fits and starts. And I think it's a little bit remains to be seen how much offshore wind we are going to be having. And so that's kind of why I put in the slide and why I don't really bring this up when I'm thinking about what's our future, right? When we're thinking about trade-offs, it's not that it doesn't exist, but it has not been moving forward in the way that the others have in terms of onshore and solar. All right, so this goes back to that Maguire report that I talked about, and this is thinking about utility scale solar and specifically in rural areas. So rural areas essentially use the Census Bureau information to eliminate high density urban areas, population density. And then we're going to see where solar panels are across the US in the rest of the country, right? And so what we found was through 2020, 74% of solar farms and 93% of solar capacity were in rural areas, right? So if you're looking here, we also can see, you can't so much see the rural areas, the scale's just not going to show it to you, right? But you can see that we do have a lot of solar going on in the Midwest. I will tell you, which you may not be surprised by this graph, Minnesota has some policies promoting renewable energy, particularly solar development. And so that's one of the standout states. Also, we see North Carolina over here in the Atlantic, right? So we do see solar along the areas where we saw all of that solar potential. We also see solar development well up farther north, right? In part because one, it's, you know, when you're thinking about solar potential, it depends on the month, right? And how sunny it is. And there's just a lot of solar potential across the US. So we see a pretty wide distribution of solar panels. The other thing you'll know is that yellow dots are the predominant dot, right? And that just shows you how new solar development really is. So these are the utility scale solar farms, right? So 2020, it was 45 gigawatts of solar, right? By 2023, right, we were at 93 gigawatts. Now that's the entire US, right? But in 2020, the entire US was at 48 gigawatts. This 45 was in rural areas. So huge growth here, right, in terms of capacity. And then solar's growing faster than wind. After 2025, The EIA, at least as of 2 years ago, was forecasting that 75% of renewable growth is going to be from utility scale solar. So big growth in solar, wide distribution. Yes, the Midwest is a part of this, right? So when we're thinking about solar in the Midwest, we're having this talk for a reason, because while there has been some solar that's been here a bit older, right, say 2011 to 2015, the bulk of it is the yellow dots, right? The growth that we're seeing more recently and this expansion in the Midwest. And we'll come back a bit more to see the Midwest compared to the rest of the US in a couple of slides as well. Oh, here's one. So I went out to the internet and I said, tell me where the Midwest is. And it decided that this was the Midwest. And so I decided that there probably isn't one definition of the Midwest, so let's have two. So if you're going to define this as the Midwest, which I like, right? I'm in it. Here I am down in Kansas. Then we could compare this Midwest compared to the US. So let's do, again, thinking about the share. So we know that for the US as a whole, it was getting up to just over 7%, right? If we go that 2014 number, well, let's compare what's going on in the Midwest. And basically nothing, 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 right? And then we see this rapid jump, right? So this 2023 bump that happened in the rest of the country happened here. But right, in terms of the share, it's still quite low, right? So just over 3% here in the Midwest in terms of the share of total electricity capacity that's coming from solar. So does that mean we have a lot more growth opportunity in the Midwest for solar? Or does that mean that solar doesn't have as much potential here as it maybe does in Arizona and California? And so we wouldn't expect solar, right, to continue on this trend. Questions, right, that we have to sort of think about in terms of if we're going to continue expanding solar in the Midwest, right? Does that make sense in terms of our solar potential? It may. We do have a huge amount of solar potential in the US. And should it be utility scale, right? Should we keep thinking about this sort of large scale solar farm kind of expansion of solar in the Midwest? And what does that mean in terms of communities? What are our trade-offs? That wasn't great. Hang on. Okay, so let's do a different comparison. So let's think about small scale versus utility scale. And here we're going to do Midwest small scale solar. And this is not in a share. This is just in gigawatts. And then we're going to do Midwest utility scale solar, right? Again, in gigawatts. And what we see is small scale solar started first, actually, right? So if we go back to 2014, we really only had small scale solar. But what we see much more rapidly is that same trend we saw in the beginning for the US, where the share of small scale solar, right, compared to utility scale, right? Utility scale is clearly outpacing it. So when you're thinking about this, right, if you're thinking about some of the community concerns, maybe about utility scale solar and land use or agricultural land, then you may say, oh, we should do small scale. Another way to think about this is there's probably a reason that utility scale is growing so much faster than small scale. Maybe, right, this one is more cost effective, right? And what we're seeing, if we look at some of this data, and this is a bit busy, but I think it's important to do sort of a comparison of costs, but also to use the detailed information that NREL provided to kind of look at where are the cost differences between utility scale on the left and small scale on the right. So, and they measured this in DC, so I just stuck with that. So they have total cost numbers. Utility scale, 1,161 per kilowatt. Small scale, 2,682 per kilowatt. And this was for first quarter 2023. And this was modeled costs. They're modeled market prices, so MMP costs from NREL. And you can see here, I have the citation. Right? So what we see is that one, right off the top, small scale solar is a lot more expensive than utility scale solar per kilowatt. Then we can start to think about why, like what is different. And one of the ways I think it's interesting to think about is if we look at the share of the total percent of the cost that comes from each of these sections. So for instance, if we start actually at the bottom, when we look at the module costs, so the actual cells, right? They add in other capital equipment, and then they also have some information on electricity, depreciation associated. So just a lot of costs that go in this module box. If your utility scale, 32% of your costs come from the actual modules. If you're small scale, it's 13%, so much smaller. What we see is that there are a lot higher costs in terms of the top column here, or top row, which is soft costs. Warehousing, logistics, interconnection, outreach. I put etc. in here. There were a lot of different costs included here, and I wanted to get the sense of it without totally overwhelming the slide with numbers. And what we see is small scale, 54%. So, and then large scale, utility scale, we see 37%. Part of this points to something we call economies of scale, which is that as average costs, as quantity increases, average costs fall, right? So our per unit cost is going to fall as we increase the size of the project. That's one way that we would define economies of scale. That clearly looks like that's potentially what's going on in terms of some of these soft costs, right? That they're a lot higher for these smaller projects. But then, right, this is one look at this, right? And it's also possible to look at this and say, well, how do we bring these soft costs down, right? If we want to think about trade-offs, clearly lower cost options make more sense, right? In terms of rolling this out. But understanding where those costs come from also, I think, is helpful in trying to understand what is it about utility scale versus small scale that's having these higher costs with utility scale. And I bring this up because of the concerns about land cover change and farmland loss that are associated with utility scale that aren't associated with small scale. I also mention it because there's a lot of transmission line that has to go in, whether it's utility scale solar or utility scale wind. And if you're talking about small scale solar, then you're producing electricity at the location where it's being consumed, right? Or at least potentially you are. And so this is looking at the costs for each installation. But the question really is thinking about the full costs, right? And considering what I mentioned earlier, these sort of externality costs, right? And thinking about if there are negative externalities associated with one type of energy, right? Can we think about how to include that so that when we're evaluating the trade-offs, we're taking into account the full benefits provided and the full costs, right? It's not easy to do, but it's something to keep in mind when we think about how we might want to move forward, right? With moving towards renewable energy and electricity generation. I also want to mention wind, and then we're going to come back to this idea of trade-offs again between the two types of solar. And I've mentioned wind began in the 90s, but I think this is a nice little colorful graph to kind of highlight that. So before we move away from thinking about growth, one last nod towards growth, you can see that, you know, the colors start here, kind of pinks and reds, moves up to yellows. And there's just a lot less yellow on this graph. So there's a lot more wind. And also you can see in this definition of the Midwest, or that larger definition, which includes the plains over here, there's a lot of wind development here. And we have this high area right along the plains of wind potential. So wind clearly is also a player in the Midwest. When we're thinking about changing over to renewables and electricity generation, we certainly are going to be thinking about how we want to do that, wind and solar, some combination, in exactly the same way that NREL does these projections going forward, right? They're thinking about combinations of different energy types, renewable and non-renewable, and how does that get us towards this net zero greenhouse gas emissions. Another thing to note, if you're interested in rural areas, was that wind is almost entirely in rural areas. So 99% of wind turbines and wind turbine capacity were in rural areas through 2020. And you can see we still have this growth going on. It's just not as dramatic. So from 2009 to 2020, we went from 35 gigawatts to 119. There was a big growth here, right? Before, I started before solar. And then we got up to 2023, and again, growth continued, right? So 148 gigawatts. And as we saw in that first slide, 11.6% of US capacity. And we do see a lot of tie-in. Unlike with solar, where there's so much capacity across the US, it's somewhat difficult sometimes to predict where solar is going to go because the potential is high. With wind, you really do see this tie-in with wind capacity and that variation regionally based on wind potential. But again, that could change with technology. You could either, again, have smaller turbines or larger turbines, and then the wind potential is going to be measured, right, at 120 meters or say 80 meters, and that could give us a somewhat different distribution of wind turbines in the US. And I want to mention footprints and put a little bit of math behind them. So when we think about footprints of solar and wind turbines, we, in this publication, went looking for other work to come up with numbers so that we could give an estimate for how much of the US. Remember I said it looks like there's all solar panels all over the Midwest. How much is it really taking up? Well, the answer is in 2020, just over 400,000 acres. And there's about 89 million acres in farmland. So it's very small, right? Far less than 1% of the land was actually had a wind turbine, right? This is just thinking about the footprint of the turbine or the footprint of a solar farm. So solar farms, obviously the bottom of this photo, you can even see, right, much more close together. So we measured the footprint of the solar farm, the turbine. We use literature to just think about the footprint of a turbine. And then we looked at the amount of capacity that was in rural areas in 2020, how much acres per megawatt, and from that we can calculate the acres. So when we think about trade-offs, again, I think scale matters, right? Here we're talking about a very, very small area of land, keeping in mind this is the footprint just of the solar panels and the wind turbines, not transmission lines, right? Not any other infrastructure that would need to be put in place. But it does give you a sense of scale to say, at least in 2020, we have a lot more solar potential, we have a lot more wind potential, and we do have a lot more land area across the US where we could be placing solar farms and wind farms. And why might we not be doing that? So I just want to come back to community concerns. And NREL has put together a database of solar and wind ordinances. So this is for solar ordinances, and I just did a quick cut and paste off of their webpage because they already made such a pretty picture. But you can see that they have broken things down by property line setbacks, moratoriums, or bans, and you can see, yes, we do see some of these things happening across the US. And we can see some of these things happening in places where we see that there was a lot of solar. But we can also, of course, see that there's a huge amount of area where we don't have these. One of the reasons you might expect to see zoning or bans is because of negative externalities. So if, right, communities are feeling that the benefits and costs that are being imposed on them, right, as somebody who maybe isn't hosting wind or solar, are not being fully taken into account, they may think about how can we then, right, make sure that the benefits of these, right, or the costs that these are imposing aren't too high. And one of the ways they could do that would maybe be with a zoning or a ban. Is that a good thing or a bad thing? Don't know, but it is one thing that we would expect to happen, right? And so one of the things when we were thinking about writing this land cover paper was to say, well, one of the things you really need when you're trying to figure out policy and the impacts of different renewable energy technologies in your local community is information, right? And so understanding the land cover change better was one of our goals so that people can have more information. And I think this is going to be a key thing going forward. What do we know about the local impacts? What do we not know, right? And there is still a lot that we don't know. If you look at wind, Might say, oh, people dislike wind more, maybe, or maybe wind's just been around a lot longer. But what we do see is there is some overlap, right, where we see ordinance and wind, but there's also areas where we have a lot of wind and not a lot of ordinances, right? So there is definitely a representation, I think, of community preferences going on here. This was something from the land cover paper. I don't want to delve in it too deeply, but I do, for those who are really interested more in this sort of ag space, I have a couple here. Also thinking about the Midwest. So if we're thinking about where is solar, what was going on with that land before the solar project was put in, mostly in the Midwest, it was cropland. The shared development on cropland 43, continuous cropland. So we measured these in 3-year increments. So that just meant that it was in crop, corn, soybean, corn, as opposed to say corn, fallow, corn again, right? And we measured those separately, thinking about whether there would be some differences. I'm not going to get into it today just in terms of time, but you can see that across all regions, right, we see a lot of continuous cropland, crop and fallow. So you can think of these as agricultural. You can actually go agricultural all the way till you get to that gray line, right? So largely solar is being placed on agricultural land. And if you look in the Midwest, although that forest line is almost gone, right? It's the Midwest. But if you scroll up here, right, you can see that pattern does play out, right? Across most of these areas, most of the forest was in Atlantic area, right? Not too surprisingly, but clearly ag land, right, was the predominant place and where we were seeing solar projects and also wind projects being placed. And what did we see in terms of land cover change? If it was in agricultural before, so cropland and pasture range, those are our 2 measures of ag land, about 15% of the land around a solar farm left agriculture in the 3 years after. That means 85% of the land around solar farms was still in agriculture in the 3 years after development. For wind, it was almost 0, right? Less than 1% here. So on average, it was 0.5. So for wind, we just see this complementarity between wind turbines and agriculture. Put a wind turbine at the edge of your field, you can still farm around it, you can graze around it. Some folks were thinking, oh, well, you put in solar panels, you clear the land, you put in solar down, then you're going to clear out the ag. Under the panels, yes. But around the panels, what we found was that commonly that land remained in agriculture. Right? We did see more land cover change on solar land than we did on wind, but we also found that solar and wind lands were just sort of fundamentally different types of land before the solar panels or wind turbines went in. And part of that is they're just distributed across very different parts of the country. So solar less commonly sited on ag land, although still about 70%. For wind, it was greater than 90. Wind was consistently co-located with agriculture production, crops, including commodity crops. We'll come back to this with agrivoltaics, and then of course, pasture range land, livestock grazing. And I'm going to skip because I want to get to agrivoltaics. So I'm just going to skip one. So what's an alternative if you are thinking about rooftop solar and you're thinking about utility scale solar? Then certainly you also have considered agrivoltaics. And if you haven't, then maybe you're like me. A few years ago, I didn't know it was a word. So what does it mean? Initially, it was let's take agriculture production and we're going to put solar panels over the top of it. So it could be crops growing under solar panels. It could be livestock grazing under solar panels. What we see today in reality is that most of it is what's seen in this picture, which is some kind of grass or native grasses that are going to be grown under or throughout the panels. And it's typically thought of as pollinator habitat. So the instances of actual crop production and livestock grazing are not that high. Why is that important? If the land use concern is specific to agriculture and you're concerned about agriculture shifting into solar, does it count if that solar comes with pollinator habitat, right? Or do we really want only agrivoltaics to be called agrivoltaics and if it has crop production or livestock grazing. Different folks are on different sides of this, right? But I do think it is worth noting that there has been a lot of policy promotion in some states to say, we don't want to just clear the ground under solar panels, right? We want to think about how can we provide environmental benefits potentially and agriculture. All right, so is it a solution? I'm going to focus on the second bullet. The median size of a solar farm in 2020, a traditional one, in 2021 was 20 megawatts. At the time, the largest agrivoltaic system with crop production was a blueberry farm, and it was 4.2 megawatts. And it was a blueberry farm in Maine. So it wasn't as if all blueberry farms were moving along, right? And it was wild blueberries. So there is a scale question, right, in terms of agrivoltaics. It's also typically limited to specialty crops because it costs money if you're going to raise or space the solar panels, and they can be damaged by machinery. But you have this potential for, right, this co-location, which maybe takes the pressure off a bit of the concerns about ag land being replaced. That could give you either agricultural benefits or environmental benefits. So here's some numbers, right? If we look at 550 AV sites, February 2024, 414 were pollinator habitat. 70% were less than 5 megawatts. All systems also had higher average costs, at least from this resource, this paper that I'm citing, than traditional solar PV. The lowest cost was with grazing or pollinator habitat, and the highest costs were with crop system. So again, costs are going to be determining the distribution of these agrivoltaic sites. Although I love this picture with all the sheep, if you live in Vermont, you might get to see that in real life, right? So that in certain parts of the country, sheep grazing with panels has taken off. I will note that it's sheep grazing, and there's been research ongoing and underway to try and figure out whether cattle can also be grazed cost effectively under solar panels. And again, you would have to raise them higher. And I also want to show some research findings in this space to give you some food for thought about trade-offs and the state of the research on agrivoltaics. And the reason I'm just pulling in sort of a smattering here is because there are a lot of different findings and it's still early days. So it's somewhat difficult to make conclusions. So there was a study and they looked at native grasses. They found that it increased pollinators, increased water retention and carbon storage as compared to bare soil. It seems pretty good. Then there was an increase in late season biomass. So there was more pasture grass cover and soil moisture. Right? Oh, but then another study said, well, actually what happened was the shade from the solar panels reduced the amount of pasture, but they think the quality of the grass was higher. Although there's another study that said it did increase floral abundance, but it delayed bloom timing, right? And pollinator abundance again went down. Why? Shade, right? So sometimes shade is good, sometimes shade is bad. Soil carbon and nitrogen were lower and precipitation accumulated beneath the edges of the panel, the rain runoff, right? Another paper saying shade can be bad, and here's where the commodity crop questions come in. Corn yields went down. Corn, wheat, not typically shade tolerant plants. So some folks have started concluding that agriculture may be suited for specialty crops, berries, fruit, wine grapes, or organic specialty crops because they have a price premium. And to date, AV systems with commodity crops haven't not been proven to be feasible, but there is research ongoing. So I think it's safe to say early days, right? We have questions about agricultural feasibility, what can be grown, and then also what can be cost effectively grown. And I think there's a lot more work that needs to be done in those spaces. And I'm not the only one. Both DOE and USDA have kicked off several new research projects focusing on this, thinking about for this DOE, there's 8 million just focused on benefits of agrivoltaics to farmers and rural communities. DOE's been funding research in agrivoltaics for several years now. USDA had a big NIFA grant, and there's 3 new research projects on our agricultural research service And I think at least 3 more in the works. And what they're focusing on is thinking about commodity crops, grazing of larger livestock, right? How can we really co-locate these two things? And I think there's a lot of work ongoing. There's some answers and a lot more needed, I would say. So just a series of questions you might think about. What types of crops can be grown, right? What are the benefits to agriculture of that vegetation? Is it close enough to crops to actually help with pollination? Is grazing of cattle feasible? And can they be scaled up? So lots of trade-offs to think about on the different types of solar, different types of renewable energy, different costs, different footprints, different benefits. And so there's a lot of potential paths forward and a lot of interesting questions and hopefully some interesting answers forthcoming as well from researchers.